lecture 22. So far we have seen how one might find the transfer function of an all pole low pass filter, and how one might realize it as a cascade of biquads, and where each of these biquads is realized using transconductor capacitor structure, often called also a GMC type realization. Then we saw that given that these GMC structures are active, there is bound to be a limitation on their linear range, and they also add noise, and therefore one now needs to talk about the dynamic range of a filter realized using such techniques. And we saw how one might actually optimize the dynamic range by what is called node scaling, and we are therefore in a position to implement something which is reasonable. We also talked about how one might order biquads if you had a high order filter, and with this we are in a position to design a cascade of second order section based all pole low pass filter. One other topology that we have seen when we talked about passive network synthesis is the ladder structure, right. So, when we wanted to realize a high order filter, in the passive case one cannot realize it as a cascade of biquads, because one would need some kind of voltage controlled voltage source or something like that in order to prevent the loading of one section on the other, which will change the transfer function. So, in the passive case, the only structure that we looked at which was capable of realizing a high order transfer function was the ladder filter. You have an LC ladder and then terminated on both sides with equal resistors. We also saw that such a ladder has got some very nice sensitivity properties, in the sense that at the passband maxima and everywhere in general in the passband, there is either zero sensitivity to component variations, or there is low sensitivity to component variations, which makes the ladder a very attractive candidate for realizing high order filters. So, as a small additional point, I would like to answer the other obvious question, which is, okay, we saw how to realize a big transfer function, break it up into a cascade of biquads and implement it using transconductor capacitor structures. Is it possible to do the same thing for a what? We realized a second order section with GMC structures. Now we have a higher order. We also, again to refresh your memory, we saw that a second order GMC section is emulating what kind of passive structure? So, you can think about it as either emulating a parallel RLC network or a series RLC network. Both of these are second order structures. Okay. So, now the question one can ask is, okay, for a second order structure we found an equivalent GMC realization. The question is, can you find a GMC realization for a general high order ladder structure? Correct? So, let us see what we can do there. Again, let me quickly remind you that if you had an RLC network like this, okay. Let me also purposely number these as L1 and C2, the reason for choosing this nomenclature will become apparent as we go down the line. A GMC structure which behaves like this is the following. All right. Here I have chosen all the transconductors to be identical, correct? In which case, what can we say about C1? In order for these two, what is the DC gain of this character? DC gain must be 1. What about the DC gain of the active realization? It must also be 1. Okay. All right. So, how must one choose C1 in order that the center frequency of this structure and this structure are the same? Okay, looking back from here, how does it look like? No, don't jump. Yeah, how does it look like? R and C in parallel with a current source of value G times Vi. Okay, now if you look at the circuit from here, how does it look like? A current source, a resistor, a conductance and a capacitance are in parallel. So when you look at it at the other end of the gyrator, it looks like a voltage source in series with an impedance in series with an capacitance becomes inductance, conductance becomes impedance, current source becomes voltage source, current becomes voltage, series becomes parallel, correct? So if you terminate a gyrator with a current source in parallel with a conductance in parallel with a capacitance, how does it look on the other side of the gyrator? It will look like a voltage source in series with a resistor in series with an inductor. Okay, and what is the value of the inductance? C1 by G square. All right, and what is the value of the resistance? Is G divided by G square, correct? So it's a resistor of value 1 by G, and this voltage will be Vi. Okay, and this is C2. Does make sense? Okay, and inductor current in this network is stored where in the active realization? It is stored, so IL and VC1 are proportional to each other. They can't obviously be equal to each other because they are of different dimensions. So what is the constant of proportionality? Okay, VC1 must be what into IL1? Yeah, what might be that impedance? All right. So as far as C2 is concerned, it is looking at a voltage source in series with an inductor of value C1 by G square, and the current that flows through C2 in this passive network is IL, and in this network we see that this current is nothing but G times VC1. In other words, the inductor current in this network is being stored as the voltage across capacitor C1, and the constant of proportionality relating the inductor current in the passive prototype to the voltage in the active network is 1 by G. In other words, VC1 times G is IL. Is that clear? Okay. Now, so we have understood, and what should L1 be, by the way? How should you choose C1? Very good. So you must choose, if you want the active network to emulate the passive network completely, then what you want is to choose C1 to be G square L1. Correct? This way the omega naught of both the networks is the same and the Q is the same. Okay. Now, what is the, so in other words, we know how to figure out this part, right? But how does the general ladder network look like? Another inductor, another capacitor, right? Another inductor, another capacitor, right? And finally, perhaps a resistor. Okay, so what order filter is this? Sixth order. Does it make sense? So L1, C2, L3, C4, L5, C6. That's why I call them L1, C2, L3, C4 and so on, so that the last one tells you what the order is. Is that clear? Okay. Now we know how to realize this part. Okay. We need to figure out how to realize this guy and this character. Right? Once we realize each of these in active forms, then hopefully we can put them together to realize the entire ladder. That's the idea. Okay. Now this we know. Let's now concentrate on some active realization of this chap. This is nothing but the original LC network. Topologically it is the same thing, except that there is no R. If there is no R, what is R? R is 0, isn't it? If you take this character and put R equal to 0, you will get simply an L1 C2. Okay. So in other words, this must look like C4 L3. Okay. So we want zero resistance here, correct? So in other words, a zero resistance in series of an inductor can be realized by a zero conductance in parallel with a capacitor terminating a gyrator, correct? Please recall that whatever you have at one end of the gyrator, the other end will look like the following. You just simply replace capacitance with inductance, conductance with resistance, or you can leave conductance as it is, and series with parallel. Okay. So here we saw that we will like to have a capacitor in parallel with a conductance in order to realize a resistor in series with an inductance. Okay. So what should you do now? If I want to realize simply the inductor without the resistor, I must have what should I put? Okay, the damping transconductor is not required anymore. Okay. All right, because having an inductor without series resistance is like simply having no loss in the network at all. In other words, another way of looking at it is that the quality factor of this circuit, what is the quality factor of this character? It's infinite. Okay, what is the, why is it infinite? Okay, both the poles lie on the j omega axis. Okay, another way of looking at it, if you want to go back to your high school physics, it is quality factor is square root of, in a series network, what is quality factor? Okay, in a parallel RLC network, what is the quality factor? R divided by square root L by C. Okay, in a series network, it is square root L by C divided by R. Okay, so in this case, it's a series network. The desired series resistance is 0. In other words, you want poles to be both to be on the imaginary axis. The quality factor is infinity, which means that the LC network need not be damped, so you don't need the damping transconductor. Is that clear? Okay. So now that okay, so this is an emulation of the transfer function provided by the L3 C4 section of the network. Is that clear? All right. And what is the voltage across C3 representative of? It is the current through IL3, through inductor L3 divided by G. Everybody is clear about this? Okay. In other words, we have one contraption which is capable of realizing this, another contraption which is capable of realizing this character. Now we need to put both these together in order to get the functionality of both the passive networks cascaded. Is this clear? Okay, imagine how you would build the passive network in the lab, right? You presumably put R L1 C2 together, then you put L3 C4 together, and then join those two, and then you build L5 L6 R, then connect that up to whatever you had earlier. Is that clear?
Sir, previous case L1 C2.
All right. So, there is clearly something else that we need to bear in mind. For that, I think I have to go to the next page. All right. So, please recall that what we have done so far is just this. R L1 C2 L3 C4, correct, and we have somebody who can mimic okay. All the transconductors are G, and again C3 is assumed to have been chosen to be equal to L3 times G square. Okay. Now, this, as we discussed, this character represents that broken half. This character represents this broken half. Okay. What you will do in the lab is join these two with a wire to build the next complicated network, right. So, we had a second order network, now we will have a fourth order network in the passive structure, all right. So, then you might say, okay, C2 is like this, okay, the input to the next section is like this, so I will join these two, correct. So, is this okay or not? No, why? So, clearly what we have missed is that, see, what kind of equations are being enforced by this wire? One, the voltage across C2 is the input to the next section, right. That part of the equation is still valid, right. The input to the next section is simply the output of the first section. Unfortunately, what is not being followed here is the fact that, please note that in the passive structure, the actual current, the moment you connect this wire from here to here, the current that flows through the wire, IL3, is being removed from the capacitor C2. Okay. Earlier, IL1 would completely flow into C2. This, by the way, is IL1. Okay. After you make the connection, what is flowing into C2 is not IL1, but IL1 IL1 minus IL3. Correct? So this wire is doing two things. One, it is making the input of the second section equal to the output of the first section, right? And it is removing some current from C2. In other words, it is removing IL3 from C2. Now, in the active prototype, the output of the first section being equal to the input of the second section can be very easily enforced by again connecting a wire between the output of the first section, namely C2, and the input of the second section, namely the input of that transconductor. What we cannot do, or we have not done so far, is do the other part of what the wire, do the other part that the wire was doing earlier, which is remove IL2 from C2. Correct? Okay. Now the question is it possible at all for us to find what IL2 is? IL3 is. We need to remove, please note that we need to remove IL3 from C2. Correct? Right now what is the current flowing into C2 in the active prototype? IL1, which is G times VC1. Correct? Alright. Making the connection from the output to the input of the next stage does not violate that, as we have it. Is that clear? What we need to do is subtract from C2 a current which is IL3. Okay. So, any suggestions? We already know that this node potential is proportional to IL3B, and what is the constant of proportionality? 1 by G. So this is nothing but IL3 by G. Is that visible? VC3 is IL3 by G. Correct? We need to subtract IL3 from IL1. In other words, we need to draw out a current which is, how much current should we draw out? IL3. Okay. And though we don't know what IL3 is, we have a voltage which is IL3 by G. So how will you know the voltage? You have a voltage IL3 by G, you want to generate minus IL3. So what will you do? Minus G. Okay. Does it make sense? Alright. Now what do we have? We have this voltage being the same as this voltage, and the current through C2 is now IL1 minus IL3. In other words, loading effects are taken care of. So in principle, therefore, this emulates this passive structure, the fifth order passive structure that we have drawn. Pardon? Yeah, sure. I'll come to that. Okay. So if I redraw the circuit, make it look nicer. Okay. So this is nothing but a fancy way of drawing the earlier picture, and if you kind of think about it this way, as far as C2 is concerned, this part is emulating C2 L1 R, and then you can think of this as emulating a floating inductor, L3. Okay. Right. So, this kind of realization is often called the active ladder approach. Right, where the idea is to emulate the same kind of equations that the passive ladder imposes on the network voltages and currents, except that you now have active elements which enforce these equations. And if you kind of think of each of these transconductors shaped like a frog, you can see that each frog is trying to catch the tail of the other frog and so on. So, also called a leapfrog filter. Okay. And since this emulates the same kind of equations as the passive ladder, it must follow that it will inherit the same low sensitivity properties of the passive ladder. Okay. So, then but can you comment on this approach versus the other approach where we just split it up as a cascade of biquads? Do you think this is easier to design or that's easier to design? Well, I guess it's just a matter of putting, I mean, the only difference between a cascade of biquads approach and this kind of approach is, no, it's not even one more GM. Please note that if I wanted to convert this character into a cascade of biquads, what would I do? I mean, I won't have this transconductor at all, correct? Instead, I will make that the damping transconductor for the second one. Okay. So, as far as the economy of transistors is concerned, this is no better. Okay. Now, but there is a definite advantage to using a cascade of biquads in the realm of being practical, because it's very easy to debug a second order section, correct? Because how do you debug a second order section? In other words, let's say you designed your omega naught to be 2.2 megahertz and Q to be 2. When you designed the transconductors and put them in, you got 2.4 megahertz and a Q of 2.2. How will you go about fixing it? That's what I'm asking you. How will you debug it? You have a second order section with the wrong omega naught and wrong Q. They're slightly off from what you intended. So what will you do? You probably change the capacitors, right? You figure out two things to change, which will change. One will change. Rather, the combination of the two will change omega naught and Q. Okay, and you fix. You make sure that the omega naught and Q of the second order section is what you want. If you do this for every second order section and then cascade things, because the cascading process does not load the previous stage, it follows that the overall transfer function will be what you want. Is that clear? Now, if you have a ladder like this, okay, all you can do is you build the entire ladder and measure plot the frequency response, and you find that you wanted the say fifth order Butterworth, and then you see all sorts of weird ripples in the passband because it's no longer maximally flat because some capacitance values are slightly off. How will you go and debug this? So Yeah, what one suggestion is that you assume that only one part of it is active, you load it with the rest of it being the correct passive network, and you should basically be able to match tweak this property of this second order section, because you know that only if there is any problem it's only coming from your active part. You go and tweak it and so on, and then you remove this and put the next one and so on. And as you can see, it's a lot more messy than just designing and debugging a cascade of bicode section. However, a cascade of bicode section is a lot less sensitive, is somewhat more sensitive to component variations when compared to the active ladder. But there is nothing free in the world, and this is one more aspect that illustrates that. So, pardon? No, one second, let me answer questions one by one. The first question is, why is this more sensitive? That was discussed in a previous class. Correct.
Sorry, you can only go up.
Yes. This is, all that this is doing is simply emulating the same LC structure, just with inductors. That's all. With transconductors. That's all.
But other case, sir, if you have a cascade of bipods,
yes. All right. So, the active ladder or the leapfrog filter is a way of emulating the same equations that one has in a passive network, thereby hoping to inherit the low sensitivity properties of the passive ladder. All right. And ladder filters are more difficult, rather more messy to debug or test. For example, you made your active filter and it doesn't work, right? You don't know where the problem is. Now, to debug it, if it is everybody is talking to everybody else, is obviously a lot more difficult task than if they are all isolated, right? Then you can isolate the problem to one place and then debug. So, it's not impossible to debug a ladder, but I am saying it's less straightforward than debugging a cascade of bicode structure. So, these are the even though the sensitivity is lower than a cascade, in general people prefer to use a cascade of bicode simply because it is easier to design and debug. Okay. All right. Now, the last section that we want to realize is this character. And what do you think I must do to realize this? How will I modify this guy to realize this chap? Yes? Instead of C6, here I must have C6 and R. Correct? And what should I do with L5? No, I just want to realize this character. This will become C5. Is this clear? All right. And how will I hook this up to the previous section? Same old, same old. So, this, let's say, is the previous capacitor C4. All right. And what should I do? I must add minus G, connect it like this. You understand? The only difference is that the damping resistor is now across C6 rather than our usual C5. Okay. And the damping resistor can be realized using transconductors only by taking a transconductor and connecting its output to the input. Does it make sense? Okay. All right. So what you have to do to, in other words, how you would now emulate this structure using only transconductors and capacitors is to take this fellow and cascade it with this guy, okay, and make the circuit look absolutely seems fantastically complicated, right? But you know that's not very complicated at all. You know how it came. You understand? All right. So how to make friends and impress people? This is how you do it, right? Okay. So at the moment, if you want to impress your friends even more, all you do is replace every gyrator with its transistor equivalent, and then now you have 3000 transistors all doing stuff, right? And all that it's doing is emulating an LC ladder network. This is clear. I mean, going forward you will do it, so it's not really that big of a deal, right? So it just looks very complicated. But one thing I'd like to bring to your attention is a very common error which happens when people design these filters is, what do you think the most common error could be? The sign of G. Please note that in every gyrator one has got G and the other one has got minus G. Okay. If you don't make that, if you forget to put the inversion of minus G, all hell will break loose. Okay. Because poles which are supposed to be on the j omega axis will end up being in the right half plane, and you know, okay. So that is the only thing to watch out for. All right. And in fact, it won't even be stable for DC. Right, if you take a good way to figure out whether you made a goof is the following, is to realize the following, is to understand the following. If you take a gyrator and this side it's an open circuit, what should it look on the other side? Short circuit, correct? So in other words, if I pump in a current, this voltage must be 0. Okay. Now, if this happened to be plus G, you had made a mistake, for example, and put plus G instead of minus G, what do you think will happen to this voltage? And why? So, if I pump current into this node potential will tend to increase. This times G is the current pushed out here. This potential will increase. If this goes up and this is plus G, then this is pushing even more current into this node and the voltage will go up, right? In other words, you will find that when you run a DC operating point, you will find that the outputs are saturated to either plus supply or negative supply. All right. On the other hand, if you have chosen the correct signs, what will happen? If this tends to go up, this will also tend to go up. However, that will cause this guy to pull the voltage down, thereby keeping this voltage at 0. Right? The only stable point is when that potential is 0. Does that make sense? The sign of G and minus G can be interchanged. No problem. Correct? Okay. So, all right. So this is the one thing that you have to watch out for when you design these gyrator circuits, and that is that. All right. Let me take a 5-minute break and then we resume. So before we start off on transistor based realizations of transconductors, which will then enable us to realize in principle all doubly terminated ladder networks based filters as well as cascade or biquad type realizations. Let's quickly understand the effect of non-idealities on the frequency response of these filters, right? Yes.
For the Chebyshev, inverse Chebyshev interaction, we had LLC and parallel.
Yeah, we have not yet discussed filters with transmission zeros, right? These are all still all pole low pass filters. Okay. Now let's kind of understand various non-idealities that a transconductor may have. Yes, sir. Okay. So whatever non-idealities you can get, or rather if the filter misbehaves, it can only be due to the non-ideal behavior of the transconductor, right? So we now have to figure out what the various non-idealities in the transconductor are and what their effect is on the frequency response of the filter, correct? So the first thing, I mean, we all know that these transconductors are going to be non-linear. Let's remove that out of the picture. Let's try and figure out what all linear effects can, non-idealities can happen, and see what their effects are on the response of the entire filter. So an ideal transconductor has infinite input impedance, infinite output impedance, right? So now a non-ideal transconductor therefore has finite input impedance and finite output impedance. Typically it turns out that in CMOS designs, the finite input impedance is in the form of a capacitor, and the finite output impedance is in the form of a capacitor and a resistor. All right, and in an ideal transconductor, I must be equal to G times V. In a real transconductor, it will turn out that I will be some G divided by something of the form G divided by 1 plus S by omega P times V. I mean, this is just saying that if I apply voltage, the current is not instantaneous. It takes some time to build up. That's all that it's saying. And what would you want omega P to be? Of course, as high as possible, which is infinity, but it can't be infinity. So what do you think a reasonable estimate is for omega P? Of course, it shouldn't be in the passband of the filter. So this omega P, you are hoping that would be much higher than the passband edge of the filter. That's a reasonable thing to say, correct? We'll get into a more quantitative estimate of how large omega P must be a little while from now, but a first cut estimate is clearly that omega P must be much larger than the passband edge of the edge frequency of the filter, right? Okay, so let's now understand the effects of Ci and Co. What do you think happens? In other words, if I had a biquad like this, every transconductor has got parasitic capacitors like this. Okay. So what do you think that that does to the? So basically, the parasitic capacitances at the input and output of the filter appear in parallel with the capacitances C1 and C2. So the effective C1 and the effective C2 are now altered due to the parasitics. Thereby what happens? The omega naught and the Q are slightly different from what you intended them to be. So how will you fix this? So if you know Ci and Co, okay, fix is is it clear? Okay, all right. So even though capacitance at the input and output might seem like a big problem, you can see that at least a solution is possible. It's simply to tweak C1 and C2 so as to make the effective C1 and C2 what you want them to be. Okay. Now finite output impedance. What happens? Each transconductor output has got a resistor like this. What happens with if you have a resistor at the output of every transconductor? So we can see that this resistor now appears in parallel with this resistor and this resistor, and these three resistors come in parallel with the original damping resistor, which is 1 by G. So adding extra resistance in parallel is equivalent to reducing that resistor, thereby reducing the quality factor. So if the original response, let's say you had a Chebyshev filter and this was the original response with ideal transconductors. Okay. Now if all the quality factors have reduced from their desired values, how do you think the response will look like? Pardon? What else? Height of the peaks will no longer be? Yeah, so what you will get probably something like that, because the Q's are all decreasing. You understand? Okay. Does it make sense?
So why won't the ripple size be the same?
Okay. Okay. The next thing is to worry about what happens when you have finite output impedance, output resistance rather, causes droop in the filter characteristics, okay, due to reduction of Q. Does it make sense? Oh, I don't understand why. Pardon? No, I don't understand what you're saying at all. It is coming in parallel with the loss inducing transconductor, right? So all that is doing is reducing the Q from the desired value, right? So how can you fix this at least a little bit? This appears in parallel with G, right? So I can reduce G by how much ever I am expecting it to get, how much ever addition additional G's I am expecting because of finite output resistance of the transconductors. So that, in other words, I know that if I design for a Q of 5, I am getting a Q of 4, right? So maybe, so I can go and figure out how much I can design for in order to get 5. You understand? Is this clear? Okay. Now, what do you think will happen because of this resistor? This guy. This is the resistance due to the output impedance of this guy. What happens to the DC gain? How much will it be? Let's assume that this is all the transconductors are G. Let's say this is RO. What is the gain at DC? If RO is infinite, what will be the gain at DC? 1. Okay, what will be the gain now? Yeah, how much will it be? How do you get that? No problem. Got an infinite loop. Oh God. What will happen? the recorder is still